Welcome back, dear students. I hope the first basic design that we learned in our previous video on completely randomized design is understood very clearly by all of you and you are able to do the problems successfully. Today in this video, we shall be talking about the second basic design called the Randomized Block Design, which in short is called RBD, also called as two-way classification, the reasons for which we shall see in the coming slides. So we shall begin by understanding the features of RBD, then we shall go on to know the differences between this design, which is RBD, and the design which we have learned in the previous video, which is CRD, and get to know why RBD is better than CRD. So in short, we are going to talk about the differences between design 1 and 2, learn certain merits and demerits of this particular design, and then thereby go into the working rule of how to analyze this particular design. So the analysis would be exactly or on the same lines as we did a problem for CRD. So we shall follow the same structure with minute changes made. So we shall understand that analysis, logics there, and then apply the working rule to some of the problems which we shall elaborately do and make constructive conclusions as per the requirement in each problem. So let's commence with the features of RBD. The features of RBD are quite interesting. The entire land that was my experimental area, this whole area is what I need to experiment on. I divide them into R blocks where each block contains certain number of plots. So here I define them to be K plots. So what am I doing? The entire given experimental area, I divide them. This all has lot of plots in it. The entire area has a number of plots. So to understand or to analyze this RBD design, I divide the entire area into R number of blocks and each block contains k plots. So I'm having block 1, block 2, etc. block R. I'm having R blocks where every block is going to have say k number of plots assigned to it. So equal number of plots assigned to it. So I have k R blocks. I have R blocks and each block containing K plots. So can you guess the number of total number of experimental units? Yes. The total number of experimental units is K into R, which we'll call it to be capital N. So I repeat, an area containing a number of plots is taken into consideration for experimentation. I'm dividing this complete area into R blocks where every block has K number of plots. So I'm dividing B1, B2, etc. BR, and B1 contains K plots, B2 contains K plots, BR contains K plots. So the entire area now is divided into blocks and under each block you have K plots. So the total number of experimental units will be K multiplied by R. That's obvious because I have here R rows and K columns. So K into R, which is equal to the total number of experimental units. Now we have done the designing. Now comes the treatments. Suppose I'm giving you K treatments. Apart from R blocks, I give you K treatments. So say K fertilizers, K varieties, K brands. What am I going to do? These K treatments, I will assign to all these plots under every block at random. So a perfectly random manner, I will assign these K treatments to all these K plots, but with one condition that one particular treatment can appear only once in any block. So it appears only once in a block. So you cannot have two plots having the same treatment. So that's why the number of treatments and the number of plots in every block must be the same. Only then you can do it in such a manner that each treatment occurs only once in any block. So if I have here, I have say five treatments, just like you see in this example, and I have four blocks where each block is containing five plots. So the number of treatments and the number of plots is the same. So I have four blocks, each containing five plots. Now look at the order there. See, you see that A, B, C, D, E is occurring at random, and you find that they don't occur, they don't repeat. Same way A, E, B, D, C, C, D, A, B, E. So E, A, D, C, B. So they all A, B, C, D E occurs at random in all the four blocks in such a manner that no two treatments occur in the same block. So this is a condition which is levied on. So now we have now this layout, this kind of a layout is called the randomized block design, where the experimental land is divided into blocks, where each block is divided into certain plots, where the plots are given treatments, where the treatments do not reoccur in more than one plot. This type of a design is called the randomized block design. Kindly note that here we have two factors to test on, which are of interest here. When we talked about CRD, treatments were the only point of interest. We said these treatments give us this yield. Whereas here, a particular plot is assigned to a block, a particular plot is assigned a particular treatment. So if you look at one particular plot, this plot is existing in block 1 and the treatment A is given to it. So the yield here will depend on the treatment as well as which block it belongs to. Look at this particular plot. This particular plot will depend on, the yield will depend on block 3 and the fertilizer or the treatment B. So here there are two factors that are of interest. What are they? Blocks and treatments. So now that we are talking about two factors which are of interest, this particular design is also called a two-way classification. Why did we call CRD as one way? Because we had only treatments which will give us the yield, whereas here we have two factors, which is not only the block but also the treatment. So since there are two effects yielding to the final result, we will be calling this RBD as a two-way classification. These are the basic features of RBD. In this slide, let's look at some of the merits and demerits of RBD first. It's a simple layout. The number of treatments and the number of plots in each of the block are the same. It's a two-way classification. We can perform the experiment analysis even if some observations are missing. Whereas what are the demerits? The heterogeneity within the block. So we have not taken care of it. We have just taken some of the plots, put them under each block. But the heterogeneity within the block, especially when the treatment is large, could prove to be difficult for us to analyze correctly. And the shape of the experimental design is restricted to be rectangular, because here we have seen that there are R blocks and K treatments. And definitely RBD is a more efficient method than our CRD. This is a one-way classification, it's a two-way classification. There is no such restriction on shape in case of CRD, whereas the design of experimental units always in RBD is rectangular. Let us now start off with the ANOVA analysis for two factors. Which are they? Treatments and blocks. So as I told you, we are repeating that part of the feature of RBD, and we recognize that the total number of Our experimental units are K into R. So normally when we write the hypothesis, we state that there is no significant difference in the yield of the crop with respect to treatments. But here now that you're talking with respect to both treatments and blocks, we will have to define two sets of null hypothesis and correspondingly two sets of alternate hypothesis. One with respect to treatments and the other with respect to blocks in both the cases. So H naught 1 is the notation for the first null hypothesis, where we declare that there is no significant difference in the yield of crop between the treatments. H02 will be between the blocks. Instead of treatments, you're going to be using blocks. Alternative hypothesis, we will declare it as H11 and 12, where we say there is significant difference between the treatments and between the blocks. So we will have, as we remember, we calculated one F value for CRD. So here, since I have two statements to check, I will get two F values. Let's see that how. First, by rearranging the data by using a two-way table. We'll see that in the next slide. In this slide, we are showing how to rearrange the given data. We are having two factors to use. One is called treatments and the other is blocks. So one-way table is not possible like how we showed in CRD. We shall now place all the treatments along the columns. So we have A, B, etc. up to K. I have K treatments and I have R blocks. So I write the blocks along the rows. So like 1, 2, 3, etc. up to R. And these values, which I am showing now, are all given to us in the problem. This is the yield or the result of the treatment and the block. This is the result which is given to us for analysis. So my first step would be to introduce one extra row and extra column. What does the column tell me? I have called it as BI. What does BI mean? Let's look at the first row. The first row talks about block 1, when treatment A is applied, B is applied, etc., K is applied. Knowing the yield in all the K plots which come under block 1, the total yield in block 1 is written here. Similarly, the second row, the total yield of all the treatments on block 2 will be written here. So that means what I'm going to write under BI is the total yield blockwise among all the R blocks. So when I add them, what I get is the total yield blockwise by taking them along the blocks. I write that here. When the extra new row that I have introduced, say TJ I have called it, T meaning the treatment, I and J are only to distinguish, one is with respect to block and the other is with respect to the treatment. There is no other meaning for I and J. So here when I'm calculating TJ, let's look at the column. In this column, I have one treatment which is applied in various blocks. So this will be the yield of treatment A in block 1. This will be the yield by treatment A in block 2, in block 3, in block R. So when I add up all the column values, it will give me the total yield of treatment A among all the blocks. So that I will write here. This will be the total yield of B treatment. This will be the total yield of the Kth treatment. So when I add all the TJs, that will be the total yield that I get along the treatments by considering all the K treatments. So I'm sure you all will agree that whether I take total yield blockwise or I take total yield treatment wise, this number should match. That's my check to note that I have done the initial table correctly. And as we recall in CRD also, G represents the grand total or the grand yield. I am calling it by G here too. So sigma BI, that is total yield blockwise, total yield treatment wise, will give you a common G value. Moving further, let me now extend the column. So now that I have found BI, I will find the square bi square. I'm now trying to find the mean value finally. So I'm calculating bi square. Now what should I take next? Now here when I say bi's, I am fixing the block number. And what am I varying? The treatments. So how many treatments are we using in block 1, which is K? So K value, let us write it in the third column. So I have BI, which is the total yield blockwise. So this will give me total yield in block 1, the square of the total yield in block 1. This will be the number of treatments that I am giving in block 1. And this will give me the bi square by k value. By dividing bi square by k, this value will be written here. Similarly, the second row total, it will give me block 2 yield. It will give me square of the block 2 yield. It will give me the total number of treatments that I am using in block 2, and I am dividing the value of bi square by k and writing it here. So likewise, I fill up all the values for all the R blocks. So what will be the total of the last column? It will be the mean block yield. So this is I'm talking about blocks. So note that when I'm talking about blocks, what is the parameter that I'm going to have here? It is the number of treatments. So here it is block, it's square of the block yield. Here it is the number of treatments. This has to be remembered correctly. In fact, if you understand how to draw it, it's easy to note that you are not going to talk about the number of blocks, but you're going to talk about number of treatments. So bi square is the square of the block yield divided by the total number of treatments, which will give you the mean block yield. Coming to the row wise extension, Tj we have as the total yield treatment wise, Tj square. Now look at Tj, it's along the column. So along the column, what is fixed? The treatment is fixed. What is varying? The block. So how many blocks are we applying the treatment? R blocks. So that R value is written here. So when I'm taking it column wise, it is R. When I'm taking it row wise, it is K. You should understand this distinction. And then Tj square by R, and I'm finally when I'm adding up, it gives me the mean yield treatment wise. Now this two values will be used in order to find the sum of the squares. The value of n that I take, total number of blocks per treatment, is what I'm going to get sigma r, and sigma k is this. So k is equal to n is equal to k into r, we have already seen. So these two values must coincide. So you get the value of G, you get the value of N, you get the values of the means of the blocks and treatments. So making use of this three values, we now go into compute the sum of the squares block wise as well as treatment wise. Now when I'm trying to find, if you remember, recall, the first sum of the square, I will try to write it here because this table I can't carry it forward. I call it SST, total sum of squares. If you remember, we have written it as sigma double sigma Yij square minus G square divided by N. Now what was this double sigma Yij square? All these yields which are given here, I square them and I add them as we did, and then minus G square value I take from G and N, simplify, and I get this result. The next that I would do here would be, since I have both treatment and block, I will calculate what is called SS treatment. I will call it as SS treat, meaning I am calculating the sum of the squares of the treatments. Where are the treatments? The treatments here are A, B, and K. These are the treatments. So what do you think will happen when I come to this final step here? This will be the total mean treatments. What do I have here? Tj square by R. So the sum here, sum of the squares of the treatment will thus become sigma Tj square by R minus G square by N. And I have the value of the sum of the mean squares and G value, N value. So I'll find this. Next, what will it be? SS block. Now look at the blocks. These are the blocks. And what is the corresponding value? All these totals is giving me sigma bi square divided by k minus g square by n, and that will give me one answer. So when I'm looking at the blocks, please go horizontally and go to the last column, total, which will give you the mean value of the block yield, which is used here to calculate SS block. There is one more sum of square. I'll explain that in the next slide. Let's look at the various sum of squares which I just explained to you. First one is total sum of squares. We know the values. Between treatment sum of squares, I'm calling it SS treat. As I told you earlier, when I have the treatments as A, B, C, etc. up to K, then which one will you see? Tj square by R. This total is what you will see. Whereas when you have SS block, where you have 1, 2, 3, etc. up to R, then you will see going horizontally bi square divided by k. This total is what you will see. So this is important to understand. Don't reverse it, you will get a different answer altogether. And then the error sum of squares will be the total sum of squares minus SS treatment minus SS block. So we had already seen the SST earlier. We called it SSB and SSE in the CRD model. Now, since we are talking about both treatment and block, we are calling it by SS treat, which will mean as sum of the squares of the treatment and sum of the squares of the blocks. Now, let us frame the ANOVA table with all these values that we have just now explained. So this is the ANOVA table for a two-factor analysis. So we are having source of variation, degrees of freedom, sum of squares, mean squares, and the F ratio or the variance ratio. So the table is the same, but what increases here is one extra row which we write as between blocks. So we have 4 rows here: between treatments, between blocks, the error term, and the total. When I say between treatments, the degrees of freedom is k minus 1, where k is the total number of treatments. Sum of squares is SS treat, which we are finding from the table, and that's called, by using the formula, we are calling it R1. The mean squares of the treatments is R1 divided by k minus 1. Moving to between blocks, we have total number of blocks as R, so it is R minus 1. R2 is SS block, and now we divide R2 by R minus 1 to get MS, mean sum of squares of blocks, that is R2 by R minus 1. The error has the degrees of freedom as K minus 1 into R minus 1, and SS error is nothing but the sum of squares, which we are calling it as R3. I divide R3 by this product to get the mean sum of squares of the error. Now, as I told you, we have two null hypothesis statements and two alternative hypotheses. One with respect to treatments and the other with respect to block. So we have to calculate two F values. One we call it with respect to MS treatment and MS error, and the other with MS block and MS error. So first F1 value, we take it as F1, where we are dividing MS treat by MS error, provided MS treat is greater than MS error. But if MS error is greater than MS treat, it will get reversed. Correspondingly, the degrees of freedom that we choose will be based on what we write in the numerator. The degrees of freedom of the numerator comes first, and the degrees of the denominator comes second. And we are all aware, last design, we have seen the F table. We are going to use the same table in order to get the table value. Coming to F2, it will be MS block by MS error, provided MS block is greater than MS error, and the corresponding degrees of freedom will be R minus 1 and this product. And if MS error is greater than MS block, it will get reversed, and the degrees of freedom will also get reversed. So we are finding the calculated value and we are finding the table value. We are finding the calculated value for F2. We are finding the table value. So we are going to check in both the cases whether the calculated value is less than the table value or not. If F1, the calculated value of F1 is less than the table value, then we conclude that we accept H not 1, the first null hypothesis, because this is with respect to treatments. And if F2, the calculated value of F2 is less than the table value, then we accept H not 2, that is the second null hypothesis, which is with respect to the block. But if the value is greater than the table value, we accept the alternative hypothesis. It may happen that I may accept H naught 1 and I may reject H naught 2. That is, I am accepting H1 2 in the second case. So in both the cases, answers need not be the same. One could be an acceptance range, one could be the rejection state. So that can vary from problem to problem. So this is the way we complete the analysis and we judge whether there is a significant difference between treatments or between blocks. And both these analysis is done in this randomized block design analysis using ANOVA technique and F ratio. We shall now apply the same technique in simple problems. This is the last step as I explained to you before I begin with the problem. How do I conclude? I calculate the calculated values and the table value with the degrees of freedom at 5% level of significance. And if the calculated value of F1 is less than the table value, accept the first null hypothesis. And it's concluded that there is no significant difference between the treatments. Similarly, if the calculated value F2 is less than the table value, accept the second null hypothesis H02, and it's concluded there is no significant difference between the blocks in the field of the crop. But if the calculated value is greater than the table value, then we reject the null hypothesis and correspondingly accept the alternative hypothesis. So this is the conclusion we are going to make in the cases for both F1 and F2, that is with respect to treatments and blocks. Let's now begin with the first problem. Let's read it. Three varieties of crops are tested in a randomized block design with four replications, the layout being as given below. The yields are given in kilograms, analyzed for significance. So as we see here, there are three varieties of crops. He has given us that the design is randomized block design, but this need not be given. We may have to understand it from this table itself. There are four replications. There are three varieties of crops. As we can see here, the three varieties are A, B, and C. There are four replications. Replications can happen only for one time with a block. So that means when I'm talking about four replications, this is giving me a hint that there are four blocks. And as we see in this particular table, this cannot be a block since A is repeated twice. So whatever column that's given here is a block. So this is your block 1, block 2, block 3, block 4. So instead, what are we given here? The values of K. K is how many? Three varieties. That is A, B, C. R1, this is your block 1. This is your block 1, block 2, block 3, block 4. You see, ABC is repeating only once in block 1. ABC is repeating only once in block 1, block 2. Similarly in C and similarly in D. So our value here is equal to, there are four blocks. So it is 1, 2, 3, and 4. And so what are the total number of experimental units? It's K into R, which will be 12. This is the hint we get from this table. But the table is not very clearly given. So we will have to rearrange this because you don't have blocks written here. You are writing it. This is a block, this is a block, this is a block, this is a block. So it definitely needs a rearrangement, which we shall do in step 2. But in the first step, we shall define the two hypotheses. So again, he says analyze for significance. Significance between what? He has not mentioned. meaning that we have to define the significance difference between both blocks and treatments. So we shall write the null hypothesis with respect to the treatments, which is varieties here, and H naught 2 is with respect to blocks. There is no significant difference. Whereas in alternative hypothesis, there is significant difference between the varieties, between the blocks. So null hypothesis is given, alternative hypothesis we have defined the level of significance. Now let us go ahead to understand and rearrange the given table. You see, we are rearranging the table here. Rows represent the blocks. So block 1, block 2, block 3, block 4. Columns represent varieties A, B, and C. Now, if we note in block 1, we are given C48, B49, A47. Those were the values given. When you saw in the first one, we had in the first one C48, B49, A47. This was the odd first one which was given to us. So we have to rearrange it as the yield when treatment C is applied is 48. So for the first block, this is block 1. So under C, you will write 48. Under B, you will write 49. Under A, you will write 47. Similarly, block 2, block 3, and block 4, whatever values are given here, we have to rearrange them in this manner. So the given table is now explicitly written in this manner. And now we have to you construct our two-way table to evaluate the values of. We need to know what is G, what is N, what is sigma Bi square by K, and what is sigma Tj square by R. We need to know all these values. So for that we have to extend this particular box and construct some more rows and columns. But you see all the values given here are surrounded around 50. So what I can do, I can reduce the complexity of these values by subtracting 50 from all these values. So the cell value minus 50 will considerably reduce the cell values, which can be easily dealt with for further computation. We'll do that in our next slide. Now we have reduced all the cell values by 50. So we had the cell value was 47. 47 minus 50 is minus 3. 49 minus 50 is minus 1, and so on. We complete the given values and considerably the values have decreased. Now we shall fill up the remaining rows and columns. We start with the column first. Block values, the block yield. So in the first block we add up. Block 2 we add up, block 3 we add up, block 4 we add up, and we get the values of sigma Bi, and that's becoming 0. Similarly, we add up all the columns. So for every treatment applied in each of the blocks, we add up all the values, and that also gives me 0. So grand yield that I'm getting here is 0. So Bi is squared, I get Bi square. Then as I told you, for every block we are varying the treatments. Here there are 3 treatments. So I write 3, 3, 3, 3. For each block I have 3 treatments. So that becomes 12. Similarly, here I take R. For every treatment I am writing 4. I am using every treatment in 4 blocks. So I have 4, 4, 4. As I told you, these two values should coincide. So yes, it does. Then I divide Bi square by K, get this total mean, the mean of the yield blockwise, then the mean of the yield treatment wise for Tj square by K. So when I'm finding SS treat, I will use sigma Tj square by R. When I'm using SS block, I use sigma Bi square by K. Note that very carefully. Otherwise, you will make mistakes in choosing your mean yield either blockwise or treatment wise. Now let's make use of these to compute the sum of squares. Now this is the computation of sum of squares. You're already aware of this in CRD. So we are squaring all the yields and adding up all the values. G value is 0, so G square by N will give you 0 value. So SST is 36. Between the treatments, as I told you, the treatments are on the top, so you are going to take Tj square by R. So sigma Tj square by R is 8 because G is 0. And when you're treating the blocks, which is row wise, so you're taking it horizontally, and the last value sigma Bj square by Bi square by K is what is considered. The error, the SS error is just SST minus SS street minus SS block. We have got it to be 10. We have found all the four sum of squares. Time for us to substitute these in ANOVA table. So the ANOVA table that I have is between treatments. Degrees of freedom is k minus 1. K here is 3, so it is 2. Between blocks, it is r minus 1. R blocks, 4 blocks, so r is 4, so 3. Error is r minus 1 into k minus 1. It gives me 6. R1 is the value of SS street. R2 is the value of SS block. R3 is the value of SS error. I've substituted it. MS street is nothing but R1 divided by the degrees of freedom. That's 4. MS block is R2 divided by 3. That is 6. Then MS error is R3 divided by 6 again. So it is 10 by 6. Now I have all the three values. I now compare MS street and MS error. 4 and 1.67. 4 is greater. So the first F1 value is 4 divided by 1.67, which is 2.4. This follows the F distribution with what is the degrees of freedom for the numerator? 2. And what is it for the error? It is 6. So 2 comma 6 degrees of freedom. And F2 is between the block and error. Again, block value is greater. So it is 6 by 1.67, which is 3.59. And the degrees of freedom for the block is 3 and for the error is 6. So it is 3 comma 6. Now we shall find the table value for both and compare it with F1 and F2. Now finding the table value is similar to what I explained in CRD. I'm not doing it here. I'm giving you the table value directly here. Kindly you can check it with the tables that you have, as you can see in my previous video. So one from the table that we see that the F value at 5% level of significance for degrees of freedom 2 comma 6. So I'm sure you would remember you take 2 along the row and then 6 along the column, and this is the value that you will have, which is 5.14. Similarly 3 along the row and 6 along the column. So if I take 6, so this value here will be 4.76. So we find that the table value, calculated value, which is 2.4, is less than the table value, and therefore the first null hypothesis is accepted. So it's H not 1. That means there is no significant difference in the yield between the varieties or treatments. We also find that the second F value, calculated value, so this is actually F1 and this is actually F2, and that is less than 4.76, and we find that it is less, therefore the second null hypothesis is also accepted. So we conclude that there is no significant difference in the yield of the crop either between the varieties or between the blocks. So this completes problem number 1. Let's now study problem 2. The following data represents the number of units of production per day turned out by 5 different workers using 4 different types of machines. So as you see, the data given to us is the number of units of production per day. And it is brought out, this production is brought out by whom? Workers and machines. How many workers? We have 5 different workers. So these are the workers and 4 different types of machines. So it's A, B, C, D. So if you could treat this machines as your treatments and the workers as blocks. So because we are using the word treatments and blocks, we will try to relate it to these words for better understanding. So we will talk about machines as treatments and blocks, workers as blocks. Test whether 5 men differ with respect to mean productivity. That means to test whether there is a significant difference in the mean productivity with regard to 5 workers, that is 5 blocks. So, is there a significant difference in the mean productivity or the yield with respect to the blocks? Is this question. Test whether the mean productivity is the same for the 4 different machine types. So it's again the same. To test the significant difference in the mean productivity with respect to the 4 machines or the 4 treatments. So it is exactly similar to how we write the null hypothesis. If we have to write it, he has not given, suppose he has not given, what would we have written as H naught 1 and H naught 2? We would have written as there is no significant difference between the mean productivity, the mean productivity with respect to, first we are talking about treatments, machines. You can write anything. You can write workers first or machines first. Anything is fine. And then the second one is with respect to workers. So we normally write it like this. He has worded it like this. Now, what is our H naught 1 with respect to machines? It is nothing but subdivision 2. With respect to workers, it is subdivision 1. But both are the same. We write it as machines first and workers next. He has asked for workers and then machines. Both are same, so we will get similarly same answers. So this way of asking the question is different, the way we word it is different, so there is no difference between in the procedure that we follow. So let's begin with the problem. So we have now stated, as I just told you, H naught 1, H naught 2. H naught 1 is with respect to machines. H naught 2 is with respect to workers. The same with respect to the alternate hypothesis. And level of significance is 5%. So the rearrangement of data, I'm subtracting the cell values by 45 to make it much less. Please note that machines are placed along the columns. One machine A, machine B, machine C, machine D. These are the treatments. I have 5 workers, which are the blocks. So BI square K. K represents the number of machines per block. So in first block, that is one worker is working with machine A, machine B, machine C, machine D. So that will be 4. Similarly, all of them are 4. So it is n 20. What does R denote? Machine A is is used by worker 1, worker 2, worker 3, worker 4, worker 5. So 5 members use machine A, 5 members use machine B, and so on. So n and n is 20. The total of BI and total of TJ is minus 80. So I calculate BI square by K and sigma TJ square by R. I repeat, rows represent workers or blocks, that is these. These are the blocks. These are the treatments. So when I want the mean treatments, I take Tj square by R. When I take the mean blocks, mean block production, I take sigma Bi square by K. I use all these values to calculate the sum of squares. So the sum of squares will be SST first. So you are squaring all the yield values, that is the production values, squared and added, you're getting 894. I'm using the values of G and N to get my total sum of squares. For SS treatment, I'm using sigma Tj square by R, which is in the lower bottom, the last row that I have. And SS block, I use the last column that I have, minus G square by N. I subtract the values from SST and get SS error. Now I use all these values in my ANOVA table. So I frame the ANOVA table. First row is between treatments, or here treatments is nothing but what? Machines. So I will write it as machines here. I have totally 4 machines. So 4 minus 1, 3. R1, which is SS treat. And I divide R1 by 3 to get this result. Between blocks, blocks are nothing but workers here. So between blocks, I have 5 workers. So 5 minus 1, 4. R2 is nothing but SS block. I divide it by 4 to get MS block. I get an answer. For the error, it is the product of k minus 1 into r minus 1, which is 12, and I had R3, which is nothing but SS error. I divide SS error by, that's R3 by 12, and I get MS error. I divide MS street by MS error because MS street is greater, and therefore the degrees of freedom that I have to check for table value is 3, 12. And for block also, I find that MS block is greater. So correspondingly, the degrees of freedom is 4 and 12. So now I have found the the calculated value as 18.39 and 6.58. I have to check it with these corresponding table values. So let's see what the table values are and make our respective conclusions with respect to machines and workers. So the table value corresponding to 3 degrees of freedom along the numerator and 12 along the denominator is 3.49. The first F1 value that we found was 18.39. It is greater than 3.49. So in that case, our null hypothesis is rejected. An alternative, this we are talking about the first one. This is F1. This is F1. So calculated value is greater than table value, and therefore we say H naught 1 is rejected. When I say the first null hypothesis is rejected, it means H11 is accepted, meaning there is significant difference between in the mean productivity between the machines or the treatments, or you say the machine types differ with respect to mean productivity. So when I use one particular machine, the mean productivity is different, is high, is low. So it does depend on the type of the machine also. The second one is depending on the workers. So there we calculated F2. So we found that F2 value is 6.58, whereas the table value is 3.26. So the calculated value is greater than table value, and therefore again the second null hypothesis is also rejected. So it's 6.58 is the calculated value, table value is 3.26, so calculated value is greater than the table value, so the second null hypothesis is also rejected. So which means the second alternative hypothesis is accepted, meaning the mean productivity also depends on the type of workers we have. So the mean productivity does depend on both the machines as well as workers. So we are not saying that the mean productivity does not depend on, it does depend. Even in practical situations, we know that it does depend on the type of machines we use, the number of workers we use. So definitely our result coincides with the reality. Let's see one more problem before winding up this video. Let's read the third problem. Four doctors each test four treatments for a certain disease and observe the number of days each patient takes to recover. So we are talking about four doctors, four treatments. The results are as follows. Recovery time in days. Discuss the difference between doctors and treatments. So look at this. I have four doctors A, B, C, D. I have four treatments. So here your K value is 4, your R value is 4. And what has he given in these cells? They are the recovery dates. That is, now the treatment 1, when Dr. A gives, it takes 10 days for the patient to recover. That's the meaning. When treatment 1 is given by Dr. A, it is taking 10 days to recover. When treatment 1 is given by Dr. B, it's taking 11 days to recover. So when you see that the doctors and the treatments, are they significantly different or are they the same? So discuss the difference between number one, doctors. That means we are saying there is no significant difference between the treatments given by doctors. Second is treatment. So the second null hypothesis is there is no significant difference in the recovery time of day in days when depending based on the treatments. We will check which of them is true for the given data. So let's define the null hypothesis 1. There is no significant difference in the recovery time between treatments between doctors. So doctors will be blocks and treatments as it is. Similarly, there is significant difference between treatments between blocks is alternative hypothesis, and we shall do the problem for 5% level of significance. So we construct the two-way table as given earlier. We take treatments along the columns here and doctors as blocks A, B, C, D. Construct BI. BI here will be the number of days taken here for treatment for recovery for by the doctor A. When 4 treatments are given separately, then BI square. Then he has given you how many treatments is the doctor giving? 4. Divide one by the other to get the mean recovery time, number of days. And that on adding will give you sigma BI square by K. Similarly, TJ, that is the first treatment given by the 4 doctors. Calculate TJ value. Note that the G value is sigma BI equal to sigma TJ. This should be common. N value R is nothing but the total summation of the treatments and the total summation of the treatment, the number of recovery days that you are calculating for by every doctor and by every treatment. So it should match. So N is equal to 16 that you have. Here it is K is 4, R is 4. So therefore it's K into R, which is 4 into 4, 16. It matches. Divide one by the other to get sigma Tj square by K. So rows represent doctors, which are blocks. Columns represent treatments as treatments in this problem too. As explained earlier, we calculate the sum of squares, sum of treatments by taking sigma Tj square by R as our mean recovery time, and SS block by taking block wise mean recovery time, and SS error by subtracting SS treatment and SS block from SST. We shall use all these values in our ANOVA table and make the required conclusions. So we write in the ANOVA table between treatments. So the number of treatments we have is 4. So 4 minus 1, 3. Between blocks, the blocks here are doctors. 4 minus 1 is 3. R1 is SS treat. R2 is SS block. R3 is SS error. And error, the degrees of freedom is 4 minus 1 into 4 minus 1. We divide the sum of squares by degrees of freedom to get MS treat, MS block, MS error. We find that MS treat and MS block are both greater than MS error. So we write down the values of F1 and F2, and then we check with the table value. Here R and K are the same. So we have the same table value to verify with 3, 9 degrees of freedom and make the respective conclusions. So we find that the table value for 3, 9 degrees of freedom is 3.86, and we find both the F1 and F2 values are greater than 3.86, means both the null hypothesis are rejected. So we are accepting both the alternative hypothesis, meaning that if you change the treatments, the recovery time changes. If you change the doctors, their recovery time changes. So it all depends on the doctor and the treatment that you are given, as in today's world, which is absolutely right, and our problem confirms the same. So this is the conclusion that we make. So these are the 3 problems which are elaborately solved for you to understand what we mean by randomized block design, starting with its features, merits, demerits, differences between RBD and CRD, and the working analysis procedure. And following the procedure, we have solved 3 sums elaborately. I hope it is understood by all of you. We need to understand the difference between the words like treatments, blocks, recognize which are the treatments, which are the blocks in each of the problem. So a little of English language is very much necessary to understand these type of questions. There, otherwise, it's a stereotype working model to be followed. Now, this was called a two-way classification. We have another basic simple model called Latin square design. So as the word square, it means there the number of rows and columns would be same. So we are going to take the shape of the design to be a square one, and then see how to simplify it, as we have be having three factors to analyze. So unlike in the case of just two factors in RBD. So let's do that elaborately in my next video. Thank you for your patience, and I hope you all have understood it and will practice these problems thoroughly to understand them. You can pull out many more such problems in any book that you have, and you can please try out in the same lines. If you have any issues, you can please contact me for further clarifications. Thank you and stay blessed.